So since that's a mouthful, let me try to explain the intuition behind that. So let's say we have 4 different leaves like this, right? And this is the segmented image. And these are different species. But if you look at the 2 images on the top, they look fairly similar in their shape. And same thing with the 2 images on the bottom. They look fairly similar in their shape. On the other hand, if you look at the 2 images on the left, they're smooth at a fine scale. And if you look at the 2 images on the right, they're sort of serrated or toothed at the fine scale. And so using that as the guiding principle, we want to be able to distinguish these images. And so if you look at sort of a histogram of the curvature values at a coarse scale, and then the histogram of curvature values at a fine scale, you can end up distinguishing all 4 of these species from each other. And so this is the feature. These are the low-level features that we use. And in particular, we do this over many, many different scales, not just 2. And we do this in a very reliable way using integral measurements of curvature as opposed to differential measures. Because one thing we found after playing for over a year and a half with differential measures of curvature is that they're very, very sensitive to all kinds of things. And integral measures are very nice. And so using this, we basically can train a number of attributes. And so the attributes we can use, well, we could use these features directly. We could also train attributes for things like lobed or non-lobed, or simple or compound, serrated or smooth. All the things that we saw in the field guide, except that rather than a human having to do it, the computer can do it automatically using these features. And then using this, again, we store all the images and the attributes in our database. And so now, at runtime, what we do is we have a new image. We extract the low-level features, extract the attributes, and then we have this composition function. And what we do here is we just look at a nearest neighbor distance between the input attributes and the attributes in the database. And we just rank them in order of that. And so when you do this on our data set, this is what you get. So this graph, here what I'm showing is that basically the top match is correct. It's roughly 68% of the time. The correct result is in the top 2 matches about 82% of the time. And basically in the top 10 results with 97% of the time. And basically by rank 20, we're always correct. So this means that if you show sort of the top 20 results, you'll always find the correct match within those top 20. So this was really encouraging to see. And so now if we carried around a laptop and had a camera and whatever in the field, we could go and with a little bit of work by running this code, we could identify trees. But this isn't very useful, right? Only we can use this. And so we wanted to get this out there for sort of general people to use, and particularly for kids, right? So I think, I certainly didn't know much about trees growing up. And a lot of it's because I remember at some point in school, we used these field guides, and it was so frustrating that I didn't want to learn anymore. And so this is sort of an advertisement. We've released LeafSnap, an electronic field guide for iPhone and iPad, and it's available now. And we released this about 2 weeks ago, and we've gotten a lot of press coverage and so on, and people really seem to like this. And so you can get this now if you guys have iPhones or iPads. This is what it looks like. We have sort of like a conventional field guide. You have all the species. So far we have coverage of the Northeast US, about 200 species. And then for each one, we have a number of images taken by a group called Finding Species, who are professional nature photographers. And these images are really beautiful. We have them in super high quality, and they're all in the app. And then, of course, you can take a photo of a new leaf. It'll send it up to our server, and you'll get back a set of results, so a ranking. And then if you find for each one, you can then look at the other images that we have, look at the tree itself. We have some text information about each species. And using this, you can make the final determination. Because usually, the leaves aren't enough. You usually need the leaves, plus maybe if you look at the tree, or if you look at the flower, or if you look at the description, you can say, oh, this is likely to be the right one. And then, of course, all of this is on the website as well, leafsnap.com. But anyways, enough advertisement. Let me just summarize my talk and talk about some future directions. So I hope I've shown you that attributes are sort of a new way of looking at conventional vision problems and really making a lot of headway on them. And in my thesis, I've looked at attributes for faces using these 4 different applications, 3 of which I talked about today. And I've started looking at other domains with things like plant identification. But where do we go from here? So I think the first thing, of course, is that we could expand this to other domains. So we could look at things like astronomical images, or 3D objects, or motion or activity recognition, or things like material classification, right? So if you want to identify what a material is, right now the way people do it is using active illumination. So you have sort of a control system where you have your material sample, and you have maybe a camera on a gantry, and maybe a light source on a gantry, and you collect all these measurements, you try to reconstruct the BRDF, and from that you try to figure out, oh, this is likely to be silk or something like that. But there's a lot of, I think there's an open opportunity to use attributes to really try to identify materials much more simply. But another thing that I'm very interested in is looking at how you can more intelligently combine these attributes with low-level features. Right? So if you have two faces like this, for example, since they're roughly in similar poses, you could just imagine doing low-level features, low-level comparisons directly. So you compute some sort of, let's say, SIF features at each point on the face, and you compare them for the two faces to say, are these likely to be the same person? The problem, of course, that we're looking at is when things don't look the same. And so in this case, if you have something like this, where he's wearing glasses in one and not in the other, then if you imagine doing a low-level comparison, it's not going to give you good results, especially around the eyes. But because we have our attributes, we know that he's wearing glasses in one and that he's not wearing glasses in the other. And so we would like to be able to do things like, based on the attributes, we mask out this part of the face, and we only use low-level comparisons on the rest of the face. And you can imagine there are much more intelligent things you could do, right? So if someone is smiling in one and not in the other, you could maybe not count them out, or maybe you could have different distance functions depending on the attributes. And I think there's there's a ton of stuff you could do in this direction. And I think more generally, this sort of leads to sort of a grander goal that I have, which is having sort of a hierarchy of attributes for robust vision. And so starting with images, vision has looked so much at low-level features and what you can do with them. And I'm starting to look at these intermediate-level attributes. But the hope is eventually to get to some sort of high-level reasoning and understanding about the images. And so to give a concrete example, you can imagine in architecture, let's say you build sort of attribute or part classifiers for houses. And so you could have classifiers for roof tiles and roof lines and lintels and window panes. And then using these, you could get higher-level attributes. So you could say, because you have a simple capital and a column, in a molded base, you're looking at a Doric column. Or because you have a steep roof and a cornice on a window, you're looking at a gable. And then using these things, you can maybe say things like, oh, this must be a Victorian house, or this house is ornate. Or maybe using other cues, you can say that this house is inhabited. And then, once you have these very high-level attributes, you can start to do things like image exploration. So maybe you could pull up, this house. Even though it looks nothing like the other one, they're both Victorian. And so once you have this sort of higher level understanding of these attributes, the hope is that you can start to extend them and start to really find cool new stuff. So in any case, that's basically it. I wanted to say that I'm in attributes. I want all of you to start looking at attributes. And to help make that easier, I've released some data sets for faces and this face search engine and LeafSnap. But that's it. Thanks. Any questions? Yeah.
This is probably a more general machine learning question, but when you have the even people making determinations about, say, who's Caucasian, there's probably maybe a very subjective opinion. So whether
it is.
Saying that they're correct or not is probably not the right thing to ask. And maybe be correct in that if they were to tell you later, yes, that person is Caucasian, it would match what they said earlier as something else, but not match what somebody else said. So are there people looking? Are you
Yeah, so definitely, we've been thinking about it a lot. There's been a lot of work from Christian Grauman's group at UT Austin looking at attributes and specifically these kind of questions of subjectivity and things like, we find this ourselves, which is that people aren't necessarily consistent on these things. And so there is no objective ground truth. There's some sort of subjective ground truth based on what people say. And we find, some attributes are very unambiguous. So things like gender is almost completely unambiguous. But But other things are much more sort of ambiguous. And the way we sort of got around it is we said, all right, if most people agree on something, we're going to say that's fine. And so what we did on MTurk was we asked people so we gave them examples of each attribute. So when we said Caucasian, we said, here are 5 examples of things that we consider Caucasian. So you should mark stuff like this. And then we only looked at the images that multiple people, like at least 3 people agreed on as training input. So, right. Yeah, so it was really fantastic. I mean, MTurk, I think it takes a little bit of work at the beginning because you have to really tweak the job that you put up so that people don't cheat on it and they don't get lazy. Because in general, people want to, right? Because they're getting money off this. And so you have to make sure that you do things like you don't you make sure that people do actually click on stuff, and you don't in fact count the results if they don't click on anything. Or things like independent verification. So mTurk makes it very easy to submit the same job to multiple people. And for different tasks, we want different numbers of people. So for something like attributes, which are fairly simple, having 3 people do it is fine. But for something like labeling the points on the face, where we need sort of more accuracy, we had to send it out to like 10 people at once. But so what happens typically is that it takes maybe a week of iteration where you submit a number of small jobs just to see how people do on it. And you find the kind of mistakes or the kinds of sort of cheating that people do, and you guard against it. And then once you do that, then it's set, and then you can send out a batch job with 2,000 faces. But it's super fast and very inexpensive and very efficient. So we've been very, very happy with it.
So specifically, follow up on that. On say something that requires fine motor coordination, some attention.
Right.
Do you have some idea of you can analyze the variation that you get?
Yeah. So in fact, on our on the face parts paper, we find that in general the part classifiers we end up training are more accurate than people are, or more consistent than people are. As far as how accurate people are, I think we have some numbers in the paper. I don't remember exactly what they are. It is sort of as you expect. So things like corners of the eyes are very, very spot on. Things that are a little bit tougher to say, like the corner of the nose maybe is a little bit tougher and people are not as good. Things like the jawline are much, much worse. And so in fact, in our paper, we don't really have the jawline. Although we did try to collect some data, but we found that was really, really tough to do, because there are no sort of defined things. And really, it's more of a curve that you want to get rather than the thing. But also, it's not a defined point, right? It depends on your viewpoint, and so you end up getting sort of inconsistent things. Right. Thanks.